Welcome back to the deep dive.
Right.
If you're settling in, maybe grabbing that last coffee, maybe something a bit stronger, well, hang tight. Because tonight, we are doing something a little crazy. We're spanning like 4,000 years in one chat. We're going to contrast the absolute, painfully slow discovery track in history with something, well, frankly, bizarre and reality-bending that basically just happened.
Yeah, it's quite the juxtaposition. We're diving into the history of invisible forces, the stuff you can't see, but, well, you rely on completely. We're talking the whole journey. From ancient Egyptian electric fish, they actually called them the thunderers of the Nile, which is fantastic.
Love that name.
Right, all the way to electrons literally playing. Well, physicists are calling it quantum pinball. This is happening in labs down at Florida State, like right now, 2025.
And that's the hook, isn't it? Electrons that are somehow frozen and melted at the same time. It just messes with your head. So our reading for tonight, it covered these two, let's say, incredibly powerful threads. First, this slow motion crawl towards taming electricity, starting way back like 600 BC.
Painfully slow is right.
And then, bam, the second thread. The sudden, explosive, really high-stakes birth of quantum physics around, 1900?
Exactly. And the mission here, for you listening, is really to dig into the deep philosophical questions that both of these journeys kick up. We want you to walk away with those aha moments, the key names, the details behind the breakthroughs, maybe grasp the sheer panic of those mathematical crises.
Right. So you can sound incredibly smart about it all.
Without needing to actually, calculate a single wave function.
Yeah, who needs the equations when you could just picture a catfish giving some poor ancient Egyptian therapeutic shock? Let's get into it. This journey into the known and, well, the totally unknowable.
Let's do it.
Okay, first up.
Yeah.
The slow burn. And honestly, just looking at the timeline here, it kind of gives me existential dread. It took us, humanity, thousands of years just to figure out how to get from a static zap to a controlled flow of electrons.
It's genuinely staggering when you think about it. It's not like the force wasn't there, right? It was everywhere, lightning, obviously, but also in the oceans, even in our own bodies. Yet for most of recorded history, it was just, I don't know, divine anger or maybe a weird medical thing or, a party trick.
Parlor trick, yeah.
It's a perfect case study in how human perception can just be totally blind to something fundamental staring us right in the face.
So let's start at the absolute beginning, the oldest interaction we have evidence for, and it's suitably fantastic and weird. Ancient Egypt. We're talking, 2750 BCE?
Almost 5,000 years ago, yeah. They knew about electric catfish, electric rays. And they respected them, hence the Thunderers of the Nile nickname. But the really fascinating part is how they used them. They were applying these powerful, totally unpredictable shocks as medicine.
Our research pointed to that, yeah. Using bioelectricity, basically raw, to treat chronic pain. Things like gout. Can you imagine? You've got this agonizing joint inflammation, and the doctor's prescription is literally go get zapped by an eel. It's wild.
Yeah.
Uncontrolled natural electricity as therapy.
And it suggests, they recognized the effect clearly, even if they had zero clue about the mechanism. We also see records much later, Roman times Pliny the Elder, noting that the shock from torpedo rays could somehow travel through something conductive, like a metal spear, and numb the person holding it.
So they saw transmission, but they couldn't, bottle it.
Couldn't bottle it, exactly. Couldn't control it.
Okay, fast forward almost 2,000 years. Greece, around 600 BCE. And we meet the guy who accidentally gave this force its name, Thales of Miletus.
Thales, yeah. He was just observing simple static electricity, rubbing amber electron in Greek. That's where the word comes from.
Oh, okay. Electron.
With fur. And he noticed it picked up light stuff, like feathers or bits of straw. So that simple little friction experiment gave us the word electricity. But, and this is crucial, it also created a massive confusion.
Right, because they mixed it up with magnetism, didn't they? They already knew about lodestone attracting iron.
Precisely. For centuries, this tiny little static zap, this power of friction, it got lumped in incorrectly with magnetism. They just couldn't differentiate the force from rubbed amber and the force from a magnetic rock. It got filed under weird attraction force, basically. And that intellectual misfiling, that failure to look deeper, is probably one of the biggest reasons for that huge historical gap.
That's the bit that just, blows my mind. 600 BC to 1800 AD. That's 2,400 years.
Yeah.
We built Rome, we had the Renaissance, we figured out gravity, for crying out loud, but we still hadn't cracked how to make a decent battery. Why? Why so long?
Well, The fundamental hurdle, I think, was the conceptual jump.
Mhm.
Going from static charge, which is fleeting, chaotic, hard to study, to a sustained current flow. You can't really harness something until you have a steady source. And that just didn't show up until 1800.
But there were some absolutely key steps before that. You got to mention Ben Franklin, right?
Yeah.
1752, flying that kite in a storm. Crazy guy.
Franklin's experiment, yeah, it was critical, not because he discovered electricity, obviously, but because he identified it. He was the one who proved that the terrifying, massive force of lightning was the exact same thing as the little spark you got rubbing glass.
He connected the dots.
Connected the dots, and that demystified lightning, huge psychological impact. But more importantly, it led directly to the first truly practical application, the lightning rod. He literally tamed the sky.
And speaking of taming, or maybe remystifying things, the story takes this really dark, kind of philosophical turn with Luigi Galvani in 1791.
Ah, Galvani and the trucks, yeah. He was looking into animal electricity. He found that if he touched dissected frog legs with two different metals, the legs twitched violently. So he concluded, maybe understandably but wrongly, that the muscle tissue itself stored this electrical energy, some kind of inherent life force or animal spirit.
Which is just pure nightmare fuel, right?
Yeah.
And it immediately sparked this ethical, conceptual crisis. Was electricity the secret to life itself? Could you reanimate dead things?
Oh, absolutely. It directly paved the way for Mary Shelley writing Frankenstein in 1818. She totally tapped into that public fascination, that anxiety about electricity being the very spark of life. It made everyone, scientists and the public, deeply uncomfortable. Where was the line between biology and physics anymore?
But that philosophical drama, it didn't last too long, did it? Because Alessandro Volta steps in around 1800 and basically tells Galvani, look, mate, cool experiment, creepy frogs, but you're wrong. It's not the frog.
Exactly. Volta demonstrated that the electricity wasn't coming from the animal tissue. It was generated by the chemical reaction between the different metals and the saltwater solution they were dipped in. The poor frog leg was just acting as a very sensitive detector. And Volta's invention, the voltaic pile, the world's first chemical battery, that was the absolute game changer. It gave us the first controllable, sustained source of electric current.
And control was the key. That was the real industrial tipping point.
Yeah.
Once you had steady current, things just took off.
Yeah.
The pace became frantic.
Completely. Michael Faraday discovers electromagnetic induction in 1831, just a few decades later. Basically, if electricity can create motion that's a motor, then motion can create electricity that's a generator. And that's when electricity went from being a scientific curiosity to being the absolute cornerstone of the second industrial revolution.
And then you get the big finale, the dramatic war of currents later that century. Edison pushing his direct current, DC.
Against Tesla and Westinghouse backing alternating current, AC.
And AC won, obviously, leading to the power grid we all use today globally. That whole transition from Volta's simple battery to a world wired for electricity, it took less than 100 years. Compare that to the 2,400 years it took just to get the battery in the first place.
The slow burn really did lead to an explosive finish. Okay, so now let's pivot. Let's look at a scientific revolution that kicked off just as that war of currents was wrapping up, the rapid revolution of quantum mechanics.
Yeah, this is the ultimate contrast, isn't it? Electricity was this slow, gradual creep. Quantum mechanics was like an intellectual earthquake. It just shattered everything almost overnight. They thought physics was pretty much wrapped up, tied with a nice, neat bow in the late 1800s. So what was the crack? What shattered that certainty?
It was something called the ultraviolet catastrophe, and it's one of the great ironies in science history. Classical physics, governed by Maxwell's incredibly successful laws of electromagnetism, tried to predict the energy radiated by a theoretical, perfect hot object, what they called a black body. And they were so confident in their math.
Okay, so what did the math predict? What was the problem?
The math predicted that as this object radiated energy at higher and higher frequencies, so moving towards ultraviolet light, X-rays, gamma rays, the amount of energy it radiated should become infinite.
Infinite energy. Wait, that's not just a little bit wrong. That's completely bonkers. We don't see light bulbs suddenly emitting enough energy to, vaporize the planet.
Exactly. It was physically impossible. It flew in the face of all observation. But the mathematics, according to the established proven classical rules, was flawless. That was the crisis. It wasn't just a calculation error. It meant the fundamental rules they were using to describe the universe were broken, at least when applied to this specific problem.
Okay, so enter Max Planck, 1900. He fixes the math, but he basically hates his own solution. That sounds like the most human story in physics ever.
It really is. Planck was a deeply conservative physicist by nature. He found the only way to make the equations match reality, to stop the energy going to infinity, was to propose something radical. He said energy isn't continuous, like water flowing smoothly from a tap. Instead, it comes in tiny, discrete, indivisible packets. He called them quanta, based on the equation E equals h nu.
He quantized energy. He broke it into little pieces. But he didn't really believe it was real, did he? He thought it was just a mathematical trick.
That's right. He saw it as a temporary fix, an act of desperation, as he later called it, just to make the math work for the ultraviolet catastrophe. He desperately wanted to believe in a smooth, predictable, classical universe. But he'd opened Pandora's box.
And 5 years later, 1905, Einstein's miracle year, he just burst through that door, Planck cracked open. Einstein basically says, Max, you're quanta. They're not just math. They're real. They're particles of light.
Yeah, Einstein took Planck's quantum idea and ran with it. He used it to explain the photoelectric effect, that weird thing where shining light on a metal kicks electrons out. Classical wave theory couldn't explain why only light of a certain frequency or color, not just brightness, could do it. Einstein showed light must arrive in these particle-like packets, photons, each carrying a specific chunk of energy.
And that idea, light being both a wave and a particle,
Yeah.
that got him the Nobel Prize, right? And it underpins so much modern tech.
Absolutely. Think about solar panels. That's the photoelectric effect in action right there. But here's the beautiful irony, the central tension of the whole quantum age. Einstein, the guy who made quanta real with photons, spent the rest of his life fighting against the inherent randomness and probability that his own work helped unleash.
He just couldn't accept it. He wanted that predictable, deterministic universe back. The famous line, God does not play dice with the universe.
He truly believed that if we just knew enough, if we knew all the starting conditions, we should be able to predict exactly what happens. But quantum mechanics was just getting weirder and weirder. Niels Bohr, 1913, he quantizes electron orbits in atoms. He showed electrons could only exist in specific energy levels, which perfectly explain why elements glow with specific colors, their spectral lines. They weren't just orbiting like tiny planets, they were locked into quantum rules.
And then the final conceptual bomb drops. Wave-particle duality for everything.
Louis de Broglie, 1924. He flips Einstein's idea. If light waves can act like particles, photons, maybe particles like electrons can act like waves. It was a radical hypothesis, but it was confirmed experimentally just a few years later, 1927. The idea that a solid thing like an electron is also somehow smeared out, acting like both a point particle and an extended wave depending on how you measure it, well, that just meant the old rules of reality were officially gone.
And the speed of that change is just staggering. From Planck's reluctant maybe in 1900 to reality itself being fundamentally fuzzy and weird by 1927, that's less than 30 years. Compared to the 2,400 years it took to get a battery, it's practically instantaneous. Okay, before we dive headfirst into the absolute latest, weirdest manifestation of that quantum reality, this quantum pinball stuff, just a quick moment. If you are finding this deep dive into history's weirdest forces and breakthroughs fascinating, please take a second to hit that like button, maybe subscribe to our YouTube channel. We're a pretty small channel, honestly, and your support genuinely helps us keep digging into these incredible, strange corners of science. So yeah, thanks so much for being here with us. All right, we've set the historical stage. Now let's jump right to the bleeding ouch. November 2025. This absolutely wild discovery coming out of Florida State University. They've theoretically pinned down this new, totally bizarre hybrid state of matter, and they're calling it the quantum pinball state.
It is absolutely cutting-edge stuff. And it all happens in a very specific, very engineered kind of material. So to really get the pinball idea, we first have to talk about the playground. These things called moire materials.
Moire. Like, when you look through 2 layers of screen door and you see those weird shifting patterns, that kind of moire.
Exactly that visual. Perfect analogy. So imagine taking 2 different atomically thin sheets of material, like tungsten diselenide and tungsten disulfide WSC and WS0 are the short names. Now stack them on top of each other. But here's the trick. You twist one layer, just a tiny bit, like 1 degree, out of alignment with the layer below it. That tiny twist creates a much larger repeating pattern across the surface. That's the moire superlattice.
Okay, so we're not talking atomic scale anymore. We've built this bigger artificial grid pattern for the electrons to live in.
Right. And that superlattice acts like a like a quantum magnifier. Twisting the layers does weird things to the energy landscape. It tends to trap the electrons in really confined pockets within that bigger pattern. And crucially, this massively cranks up the importance of how electrons interact with each other. When electrons interact strongly, they stop behaving like individuals and start acting collectively. That collective behavior is where really exotic stuff like superconductivity or weird kinds of magnetism can suddenly emerge.
Okay, so a special playground where electrons really notice each other. And in this playground, we find something called a Wigner crystal, which you mentioned is actually a really old idea, right?
Yeah, theorized way back in 1934 by Eugene Wigner. And it's a beautifully simple concept, really elegant. Electrons all have a negative charge, so they hate each other, they repel. Wigner said if you make the electrons really sparse, really low density, that repulsion force totally dominates everything else. And what happens? They spontaneously arrange themselves into a perfect, rigid, crystal structure, like a lattice, just to get as far away from each other as possible. It's basically a solid made entirely of electrons, frozen in place by their mutual hatred.
Huh. It's the ultimate electron social distancing.
That's a great way to put it. Now, in these fancy moire systems, we don't just get the simple Wigner crystal. We get something more complex, weirder, called a generalized Wigner crystal, or GWC. Because you can tune these twisted layers so precisely, the electrons don't just form simple triangles or squares. They form intricate patterns. Stripes, honeycombs, all sorts of weird geometric motifs. And this often happens at what they call fractional fillings, like when only 13 or maybe 23 of the spots in that superlattice grid are filled with electrons.
Okay, so we have this complex, frozen, very ordered crystal made of electrons, the GWC. Now finally, bring in the pinball. The headline finding is that this material is somehow simultaneously insulating, like the frozen crystal, and conducting, like a normal metal. How on earth does one system do both?
Okay, this is where it gets mind-bending. The quantum pinball state is this paradoxical phase. It's a theoretical hybrid state that represents a kind of partial melting of that GWC. And the pinball analogy is really the best way to picture this duality.
Let's break down that pinball machine picture then. What are the parts?
Right. So imagine two distinct populations of electrons within this material. The first group, they stay completely stuck, localized, frozen into that rigid GWC lattice structure. These are your fixed pins in the pinball machine. They provide the insulating backbone, the solid structure of the crystal.
Got it. The fixed pins anchor the lattice. That's the solid insulating part.
Exactly. And this is the crucial new physics bit, the whole system isn't just governed by electrons hating their immediate neighbors. It's driven by powerful, long-range Coulomb interactions. Basically, every electron feels the repulsion from every other electron in the system, no matter how far away it is. Older, simpler theories often ignored that long-range part, just focused on neighbors.
Okay, so it's a much more complex web of repulsion. What does that do?
Well, it creates enormous frustration in the system. It becomes energetically difficult for all the electrons to stay perfectly frozen in that crystal lattice, especially at these specific fractional fillings, like 13 filled. So these strong, long-range interactions, combined with the inherent fuzziness of quantum mechanics, quantum fluctuations, they basically force a certain fraction of the electrons to give up being frozen. They delocalize, they start moving freely around those fixed pinned electrons.
And those are the bouncing pinballs, the mobile electrons, the conducting part, flowing like a liquid through the gaps in the fixed insulating lattice.
Precisely. So you have this bizarre coexistence, an insulating skeleton with a conducting electron fluid running through it, all happening at the same time within the same material at the electron level. It's simultaneous order and chaos. And you absolutely cannot get this with classical physics. Classically, things are one or the other, solid or liquid, insulator or conductor. This hybrid state is purely quantum, driven by these really complex, strong electron correlations.
Okay, this sounds like a problem that, definitely requires more than rubbing amber with fur. You need serious computing power for this.
You need serious simulation overkill, which is exactly what the FSU team Aman Kumar, Cyprian Lewandowski, and Hitesh Shanglani brought to the table. This wasn't just a wild guess. They were trying to solve a real puzzle. Experimental results, especially from scanning tunnel microscopy, STM images of these GWCs in the 2D materials, they kept showing weird behaviors, inconsistencies, things that the standard, simpler theoretical models just couldn't explain.
So the existing models, the ones that mostly ignored the long-range repulsion, they were basically failing to match reality. when looking closely at these GWC experiments.
Exactly. The models were broken. So this team had to use computational techniques that could actually handle the insane complexity of these strongly correlated electron systems. They leaned heavily on FSU's high-performance computing resources.
We hear acronyms like ED and DMRG thrown around in their papers. What are those, roughly? And
Well,
why were they needed?
right, those stand for exact diagonalization, ED, and density matrix renormalization group, DMRG. And these aren't just, faster computers. They're highly specialized mathematical techniques designed specifically to model these tangled up systems where many particles are interacting strongly and classical ideas just fail completely. ED is super precise but can only handle really tiny systems, like a few atoms. DMRG can scale up to much larger systems, especially in one dimension, but with some approximations. They needed to combine results from both to build a picture of the whole system.
And they ran these alongside other methods, like classical Monte Carlo simulations, to map out the whole phase diagram, like testing all the possibilities for how the electrons might arrange themselves depending on conditions.
That's right. It was a huge computational effort, running a sort of digital twin of this quantum system to see what states could emerge. And that rigorous work is what allowed them to finally resolve the discrepancies between theory and experiment. It showed that this bizarre pinball state, the hybrid insulator conductor, must exist under the right conditions in these materials.
And the timing just confirms how new this all is.
Oh yeah, it's basically hot off the virtual press. The first theoretical preprint paper outlining this came out around September 2024. Then it went through peer review and was formally published in NPJ Quantum Materials in August 2025. And the public announcement, the big reveal, was just November 6, 2025. We are literally talking about physics that is unfolding as we speak.
Okay, wow. That was a deep dive into some heavy physics. But now we got to ask the so what question. Beyond just being scientifically awesome, why should you, listening at home, care that electrons are playing pinball inside some fancy twisted material? What's the payoff?
Yeah.
What tech does this enable?
Right, the practical side. While the biggest immediate promise is extreme tunability, this quantum pinball state gives scientists a brand new kind of playground, a new platform, because you've got this hybrid state, delicately balanced between insulating and conducting. You can imagine using external knobs, things like changing an electric field with a nearby gate, or maybe slightly adjusting the twist angle or pressure to easily push the system from one state to another.
So you could, like, flip a switch and turn the material from a perfect insulator to this weird hybrid state to maybe even a full conductor just by tweaking some external voltage.
It's the potential, exactly. And that level of fine control over the electronic state is absolute gold for designing next-generation nanoelectronic devices. It's especially exciting for the field of spintronics.
Spintronics. Okay, we hear that buzzword a lot. Remind us what that's about again. Future computing, right?
Yeah, so normal electronics, everything we use now basically, uses the electron's charge, the flow of current, to represent information, like a 0 or a 1. Spintronics aims to also use another property of the electron, its intrinsic spin. Think of spin as a tiny magnetic direction, can be up or down. Spintronics wants to use that spin state to store or process information.
So if this pinball state gives us really precise control over how electrons move and interact, how correlated they are, that translates into better control over their spins as well.
That's the idea. Better control over the electron's quantum state, including its spin. This could lead directly to things like much lower power consumption in computer chips, faster processing, maybe denser and more stable types of memory. We're talking about future transistors, future logic gates that could potentially use way less energy because they're manipulating these subtle spin states instead of just sloshing large amounts of charge around.
Which, I mean, that tackles a huge global issue, right? The massive energy footprint of computing in data centers.
Okay.
So spintronics is a big one. What else does this deeper understanding of how electrons get tangled up in these materials feed into other areas?
Oh, definitely. Anytime you improve our fundamental understanding of complex quantum behavior, especially strongly correlated systems, it has knock-on effects. It contributes to the ongoing hunt for high-temperature superconductors, materials that could conduct electricity with zero loss, which would revolutionize energy grids. It could potentially improve medical imaging techniques like MRI, which rely on manipulating nuclear spins, even things like building more precise atomic clocks. The fundamental knowledge gained from studying things like the pinball state ripples outwards.
Okay, that covers the practical stuff. Now, let's swing back to that philosophical clash that's kind of been lurking underneath this whole conversation. We talked about electricity, which, at least on our everyday scale, felt very deterministic, predictable. Flip the switch, light comes on, done. And then we talked about quantum mechanics, which seems fundamentally built on probability and chance.
Yeah, that tension is really where the deepest, most unsettling questions live, I think. Electricity, especially in the 19th century, seemed to confirm this idea of a predictable clockwork universe, like Newton imagined. Then quantum mechanics comes along, starting with Planck's reluctant quanta and Einstein's photons, and just rips that certainty apart at the seams.
And Werner Heisenberg really put the nail in the coffin of certainty in 1927 with his uncertainty principle.
The ultimate limitation, right? The principle basically says you cannot, even in principle, simultaneously know exactly where an electron is and exactly how fast it's moving, its momentum. The very act of measuring one property inevitably disturbs the other. And it's not because our measuring tools are clumsy. Heisenberg showed it's a fundamental built-in feature of reality itself.
So, if the universe, at its absolute smallest scale, is inherently random, fuzzy, probabilistic, fundamentally unknowable in some ways, how do we end up living in this macro world that seems so solid and predictable? Is everything we experience just, I don't know, an illusion of averages, billions upon billions of random quantum events somehow smoothing out into the reliable deterministic world we see?
That is the core philosophical puzzle, isn't it? And
Yeah.
this quantum pinball state we've been discussing, it's almost like a physical embodiment of that quantum weirdness, that absurdity. It echoes that famous thought experiment Erwin Schrödinger came up with in 1935.
Ah, the cat. Schrodinger's cat. Stuck in the box, somehow both alive and dead until you open the box and look. That superposition idea.
Exactly that superposition. The quantum pinball electrons are kind of like that cat, but real. They exist in this hybrid state, simultaneously frozen, like a solid insulating cat, and mobile, like a liquid conducting cat. They refuse to be definitively one thing or the other until you effectively look at them, until you perform a measurement that forces them into one state.
Wow. So the weirdness that Einstein hated so much, the probability and superposition, it's not just some abstract mathematical idea anymore. It's being actively engineered, simulated, and potentially observed right now in a lab in Florida. It makes the absurdity feel much more concrete.
It really forces us to confront how limited our everyday classical intuition is. We live in a world where we expect things to be either option A or option B, but the deepest layer of reality seems to insist that things can be A and B simultaneously until we intervene.
Which then brings up huge questions about things like free will, doesn't it? If the fundamental components of matter operate on randomness, does that randomness create the space for genuine free will? Or does it suggest maybe there's a deeper, hidden, non-local set of rules governing everything, a script we can't see? Seriously, what do you think? Comment below. Does quantum randomness open the door for free will? Or does it point toward some kind of hidden determinism? We'd genuinely love to hear your take on that one.
It's a fascinating rabbit hole to go down. And maybe to kind of tie these two big threads together, the predictable electricity and the weird quantum world, we should look at how they actually intersect in our everyday lives now. Because they absolutely do.
Oh, completely. They're totally tangled up together now, aren't they?
Yeah.
Like every single
Right.
time you use a solar panel, you're bridging that gap.
Right. The photoelectric effect, which we established, is purely quantum. That was Einstein's photon idea. That's the fundamental process generating the electric current in every solar panel out there. The predictable flow of electricity relies entirely on that initial quantum interaction, a photon hitting the material and kicking out an electron.
In the guts of your phone, your computer, the semiconductors, the transistors, they wouldn't work without quantum tunneling.
Right, exactly. Quantum tunneling is another one of those utterly non-classical effects. Particles can literally pass through energy barriers even if they don't technically have enough energy to go over them. It's because their wave nature is spread out. Without quantum tunneling allowing electrons to hop across tiny gaps, modern microchips, memory chips, they just wouldn't function. So the whole predictable, reliable world of digital electronics is completely dependent on these bizarre quantum rules underneath.
And we shouldn't forget that ancient echo either. We started this whole thing talking about the Egyptians using electric fish for medicine.
Yeah, could that ancient, crude bioelectric therapy actually foreshadow what's happening now? We're seeing this huge resurgence in modern bioelectric medicine using very precise, targeted electrical signals to do things like reduce inflammation, help nerves repair, maybe even treat diseases. It kind of suggests those ancient Nile doctors grappling with the raw power of the thunderers maybe weren't totally off base. They were using the sledgehammer version of a force we're only now learning to wield with surgical precision for healing.
It really is this continuous, sprawling human story, isn't it? This relentless quest to understand and then maybe control these invisible forces, whether they turn out to be relatively easy to tame, like industrial electricity was eventually, or fundamentally deeply weird, like this quantum pinball state.
And it's a good reminder that our most practical, everyday reality, like the lights being on right now, and our most abstract, cutting-edge theoretical knowledge, quantum mechanics, they're not separate worlds. They're intimately linked by this thousands of years long search for understanding.
We went from a Greek philosopher rubbing some tree sap with fur, all the way to physicists running simulations with billions of parameters to figure out how electrons can act like they're both solid and liquid at the exact same time.
Yeah.
Just what an incredible journey trying to decode the hidden rules of the universe.
It really does highlight that thin, blurry line between pure philosophical wonder and potentially world-changing practical utility.
So we started tonight talking about electricity and how it created this ultimate networked reality, didn't we? These huge, sprawling grids, power lines connecting continents, basically keeping modern civilization humming. And we end with the absolute weirdest frontiers of science, the quantum realm, full of superposition and this thing called correlation or entanglement.
Right. Correlation, especially long-range correlation, like in the pinball state, it implies this deep, almost instantaneous interconnectedness between particles, even across distances.
Okay, so here's the final thought, something for you to just sort of mull over as you wrap up your night. If this brand new discovery, the quantum pinball state, fundamentally depends on these long-range correlations, electrons somehow knowing about each other instantly across the material, does that underlying quantum interconnectedness in a strange way perfectly mirror the vast practical networked reality of the electrical grid that powers our entire planet? Does the weirdest, most fundamental science ultimately just reflect back of our most practical, most interconnected everyday reality?
It's something to sleep on, definitely.
We will catch you next time for another deep dive.
Yep.
Good night.